We are from Vienna. It's in Austria, center of Europe, with 12 hours of time difference between New Zealand and Vienna, so it's per definition a point which is really far away. Currently in Austria is the beginning of winter, so, and maybe you can see it on my face, I was not used to the New Zealand sun, and my reaction capability of my skin was not good enough. And this brings me directly to the topic, which is event-based low-level control, which means a reactive behavior for mobile robots. First of all, I would like to mention that this paper is one part of a research project which is called Disassembly Robotics, with the aim to disassemble Lego bricks autonomously with different types of robots, mobile robots. And my part of research is the intelligence to reason about a certain assembly and how to disassembly, and the intelligence of robots to be able to communicate with each other and negotiate the necessary steps. And in this project, Christian Schwingenschlügel, the second author, was one student of mine, did his master's studies in the field of low-level control, and he has implemented first this technology on a mobile robot, and this is what the paper is all about. But this paper, this is also another part of my research. This whole research project is embedded in an educational robotics program, and therefore the program is called Sparkling Science from the Federal Ministry of Science in Austria. Sponsors projects which has the aim to bring young students into the field of technology. And we work together with the Vienna Institute of Technologies, which is a high school especially for technology education. And therefore students, age of 17 and 18, have a major impact on the whole project, working together, implement knowledge, rule bases. I will later talk about this. And also, based on this experiments, based on this paper, did some experiments to show the low-level control, the possibility of the low-level control. Okay, now let's talk. Was already on, sorry. So, I would like to start with the motivation why we do this. I would like to explain the use technologies and the mobile robot architecture, and then I would hand over to Himanshu Mongia. It's one student, 18 years old, of this high school, who would present their results in the evaluation, experimental results, and give also a conclusion and outlook. So, let's imagine we have three types of robots, and we would like to disassemble a Lego assembly. So, what are the requirements for such robots? They should be intelligent in the sense of path planning. They should also be able to communicate with other robots about specific tasks. They should be cooperative with other robots, so they should work together at the same time on one operation. In our case, we're using the ontology to combine the knowledge of robot B and robot A through the two software agents. Okay. But with ontologies and software agents, we are able to do everything about reasoning about a specific type. So that we call it high-level control. In high-level control, it's just the planning to do something and the ability to communicate with other partners and exchange knowledge. But if you have a mobile robot, you should also control the hardware directly. In this case, in this paper, we try to implement, we have two test cases. One robot which has only one axis to lift a brick, and one robot with three axes. And the idea was to implement a low-level control which is able to capture both test cases without any further implementation of new parts of code. Therefore, we use the standard IEC 61499, which is a standard for event-based control, distributed control in manufacturing companies or manufacturing robots. And therefore we're using function blocks to control specific sensors and motor servos. And there's also a so-called function block to implement the code, the control loop, for instance. So we have just a representation for one axis, and we just multiply this for each axis we have. And then we have a control logic block which is able to handle the whole communication to the so-called high-level control, to our agent-based system. So with this part, we are able to have an event-based control, reactive control for the mechanical parts, and the direct control for the hardware of the robot. So in our case, we would like to do something like this. We have one robot which is able to just grab a Lego assembly. We have one robot which is able to hold this Lego assembly, one robot which is able to lift this one part from this assembly. So they have to work together. This part should only show the reasoning about in the software agents. And if we have such a system, we need software agent ontologies to be able to form a knowledge base, the so-called high-level control, and we need to have knowledge about the robot and a control which is able to react quickly. For instance, if you just only use the high-level control and you put your hand on a hot oven, you can reason about if you should put your hand from this oven or not, and maybe this needs too much time. So, and the reactive control should do this automatically. So that's the low-level control. Okay, so just to explain the knowledge base, we have an ontology about our robot, which has implemented all the concepts which are necessary that the software agent knows what this robot, which controls this robot, knows what this robot is able to do. And we have an ontology about the negotiation mechanisms, how this robot is able to communicate with other robots, how the messages are exchanged. And we implemented the whole system on a CVC. CVC is from the American robotics program Dipl. It's an educational robotics controller which has the same type of speed or memory like an industrial controller. That makes it pretty perfect for us to use it for our research. On this controller we have implemented the operating system Linux, and on the Java virtual machine we have implemented Jade. It's a Java agent development environment to be able to work with the software agents. Chess is a rule-based language to implement the knowledge for the robot to solve specific tasks. The rule-based is then if then else statements. And the XML should represent the ontology. So we implemented the ontology in the ontology editor Protégé from the Stanford University, but it's very difficult to put this complete ontology from Protégé on a mobile controller because Protégé needs a lot of memory. So we just decided to use the XML standard to encapsulate the knowledge representation. And we have 40 IDE which handles the IAT6 4099 reactive control, low-level control. The common, my part of research was the software agent part. The Christian Schwingenschul, as I mentioned before, the master's thesis student, just implemented the low-level control on this controller, and the students which will present after me, the student which presents after me, they have done the communication between the low-level control and the high-level control. They have implemented both systems, the high-level control and the low-level control on this mobile controller, just to make sure that you know that they are really have really done a good work. So, and that brings me directly to Himanshu Mongia. I would like to pass to you that you finish this presentation and explain the past.
Hi, I'd like to present my team to you. This is me, this is Timon Hubert, I'm the guy, these are the cameramen back there. Raphael Fierce, who's not with us today, but let's get to the test case. Obviously, I'll just add some things to that. This thing right here, from this box right here, I refer to that one as the high-level control, which does all the thinking, and the low-level control is basically just reactive and does all the hardware component-based stuff. So we implemented the framework high and low-level control, the communication between the low-level and the high-level. And once we were finished with implementing that, we wanted to show off, of course, and so we implemented test cases to prove that our technology is better than the ones we were using before. So what we did was we wanted to create a comparison between those technologies, and we took the same line following algorithm, which was just this black stripe here, and the robot should just basically follow it. And we took the same algorithm on the same robot, but with both of those technologies. So the high-end low-level control, which was implemented by us, and the high-level control, which we were using earlier. And while we was doing that, we were measuring speed data, how long does the robot take with both technologies for one lap. And we were using deviations or the error, which you can see here. This is the high level. It is pretty inaccurate. It doesn't drive straight, it doesn't drive a curve, it drives a zigzag. I'll get to why right now. So this is our algorithm. I'm sorry I don't have any formulas for you guys. I see light formulas. We just simply do it with that one. So I'll concentrate on that one because that is crucial. This is the line following algorithm. We have two sensors, left and right ones, and all they do is they look at the surface and see if it is white or black. And obviously, if both are white, it stops because it doesn't know where it is. It's not anywhere near the line. If both are black, it's pretty good on the line. It just needs to drive forward. If one is left, obviously you get that. In addition to that one, we also need to recognize when the robot is finished with one lap, because it needs to measure the time, it needs to stop the time, and count the rounds it is doing. So this one, we also implemented that. It was implemented very similar in both frameworks, but it is not very crucial. In order to resources, it doesn't get much, so it's not very important. Then goes to the video. The upper one is the high-level control, which you will see is pretty inaccurate. It does zigzags and it is kind of slow. And this is the this one uses the framework we invented. You can see here already the difference of speed. And you see these pretty nice zigzag movements because it can't update real quick. And this one is finished when this is in the half. So it's a pretty big improvement. Alright, these are the average lap times. The HLC is the one which we were using earlier. This is the one we invented. And what you can see is not only is the HALC faster, but it is also very consistent in its speed. It doesn't vary that much, which is a very good factor to have when you're working with robots. So you also have the same speed, and it does what is expected, and it doesn't change in its speed. We did 5 test cases, and each test set was contained 10 laps. So we did 50 laps in total. We did 10 laps because we wanted to see the later laps in order to measure the battery status of the controller, or how the robot works and finds itself back in again if it falls out of the track and stuff like that. So the next one, the average deviation, which is the error, the zigzag pattern that the HLC used to create. And there we have the, maybe you can see, that's just the first lap. When you finish with that, you have 10 laps, and then we can measure the deviation here, and that tells us how accurate our framework is. Because if it continues doing that zigzag, we'll have something like 20 millimeters. And as you did see here, it was pretty much a line of 10 millimeters. So we took samples across the whole lab, which were already done. So if errors occur, we can still go on thinking while the LLC takes care of those errors. And we get to the last one, minimal deviation and better performance. Obviously, we ruled out all the errors. We have a good accuracy, and because it is accurate, because it doesn't do many errors, it is also faster. And it is obviously reactive. So it can update much quicker because it's got a better performance, it doesn't do many errors, so it can react to its environment and act supposedly. Thank you. Do we have time? We have another video.
We've got lots of time.
Yeah, alright. So we can watch this and do the question part. Like
How would you explain what your robots are doing?
Yeah, well, what they're doing right now, what they're doing is it is parallel orientation, because when you're taking apart things, it is really important that you're very exact and very accurate. Because if you're 2 centimeters right away, it doesn't make sense to grab it because you won't be able to. So we have to work pretty accurate here. And now we do this layer by layer. So we've got 3 or 4 layers of blocks, and we always take off, we always leave 1 layer at the ground and take off everything on top of that. So we can work with this one. And now just check if there were 2 stones or 1 stone at the base layer. And now it's recognizing the color, because right there we've got the containers, and the robot should recognize the color of the containers of the flags and sort in the stone in the right container.
Yay!
There it is.
This was unready, it was very amplified. Okay, that is the final project of ours. Thank you.
Are there any questions?
I'm just curious. So, first of all, I just want to get clear that the strengths you're introducing is you have the integration of LLC and HLC exist in one system at the same time. So
yeah.
It will be,
they're on the same. See,
sorry.
So no.
Because what I was curious is that because you have, I'm not sure about the hardware platform's performance, but you're running a very heavy software layers from Linux operating system, JRE, and J, and beneath J there's another region runtime system.
Yeah.
So I mean, it doesn't surprise me that it cannot do that real-time operation and it generates a zigzag performance.
You go, I'll just add to it.
Okay, so we have, first of all, we have done this on a real PC with lots of megahertz and memory, but our aim is to implement our technologies in industrial controllers. The CPC you see there has 128 megahertz of RAM and 300 megahertz. And so, yes, if we just use the high-level control with the agent-based system, it takes long computation time to get a value from a sensor in the knowledge base of the robot, and then bring the software agent to reason about this new value in its knowledge base, and then set actions. It needs a lot of computation times. And just remember, we don't get get new values each second, so 10 times each 100 milliseconds. So we have to update our ontology and reason every 100 milliseconds with a lot of computation time. So maybe you have a loss of information, and that brings this zigzag thing. So we just implemented this low-level control, which is able to react quicker and make this Separation, thank you. This separation between reasoning and really operating. So just the agent-based system is just reason about the next step and told that low-level control what it should do. And this works really fine.
Actually, this is the reason why we implemented HLC and LLC on the same controller in the first way. Because we wanted that, because the HLC was not enough, it was too slow. And then we said, we want something, the HLC should think, and it should pass on to the LLC and go like, yeah, do it, deal with it, I'm just gonna think. So that's why we actually created the separation.
Just this is not a question, just probably another comment. I'm just wondering, every configure, I mean, this hardware platform is pretty much like ARM9 based, 400 megahertz. If you consider some other functional languages or synchronous programming languages like Pascal or Ada, that they have they're designed for reactive systems, and they allow you to do time analysis and all sorts of things. And probably with a real-time operating system like FreeRTOS instead of Linux, so would improve the performance already.
Yes, of course. We have to think about that. This how we implemented in this way, because it's based on a further research project which uses this technology, and this research project had the aim to prove exactly the same part of technologies on this controller. So the idea was to combine our mobile robot with we have set up a manufacturing system in our lab, which is controlled effectively with the software, but the separation between high-level and low-level control. So the low-level control is on the parts of in the manufacturing system on the controller, and the high-level control, the HSR, on a very fast PC system, on a separate PC system. And this is the first implementation to use it on one controller. The next step is, of course, improve the reaction capabilities of the software on this part. You can also use a C-based agent system, which should make it also faster than the Java-based system. Yeah, right. That's our next steps.
Was there any reason why you were disassembling things rather than assembling?
I think he would like to answer that, so I'll just say one sentence because he's all about disassembling. But we were actually really bored because all the industries, I think they're pretty good at assembling things, at assembling products, and disassembling was it just came to us naturally because we like to disassemble them, and what's behind it is the recycling part. So this is of course just research, but when we're finished with it, we'd like to disassemble a TV and then sort the right parts, the right screws in the right container so they can be used for further development.
Is it fundamentally different?
Assembling it?
Yes. It is?
Yes, it is. It is. Because
the difference is when you assemble something, you have to plan how to assemble something normally. And if you get something to disassemble, you might not have this plan. And the big difference is that you then have to reason about, maybe with the vision, with the camera system, just look at it and try to reason about the correct way to disassemble things. That's the main difference between assembling and disassembling.
The thing is, I also read in his research paper somewhere that you should probably, if a company is automating their assembling part, you should get their plans and do it accordingly. But I don't think any company has got a plan on how to disassemble their product, so it is a real difference.
And just going back to your control of the following line, that line, presumably it was an on-off control.
Sorry?
So it's on-off, and you looked at, did you have one sensor or two sensors?
We had two sensors.
Two sensors. And were they binary or were they analog?
It was analog, but we had a threshold.
So you didn't use any grey or anything like that?
No.
Okay.
It is an analog sensor, and then we decided to convert it into binary by adding a threshold and then going smaller than 511, it's white.
Okay, are there any other questions? We're a little early. I assume you come only from Malaysia, and nobody wants to give another talk.